Hi everyone, I'm Andreas, professor at the VUB, and today I will talk about LLMs. Now, first of all, I actually want to continue the celebration on welcoming Sophia. And actually during this talk I will explain why I'm excited about Sophia being part of the VSC now in 3 parts. Can I actually also use that one? Okay.
If you put it on.
Okay, but I'm actually afraid that it will. Okay, does this? Okay, this also works. It's more comfortable. Sorry about that. Okay, and I'll actually explain why I'm excited in 3 parts. First of all, I'll give a brief recap or intro into LLMs in my own style, just to make sure that we all are talking about the same things. Then I will talk about the research we are performing in our lab. And finally, I'll conclude with some future outlook, which of course goes beyond our lab. So I'll mostly be talking about researchers who code, who I believe is the majority of people here in the room. So what are LLMs? Well, I think all of us have heard about them right now, but again, I'd like to give my own style of introduction, because then we are essentially talking about the same things. So LLMs, also known as GPT, Generative Pre-trained Transformers, it was a term coined by OpenAI in 2017 when they were doing still mostly research. Afterward, they have used this as a commercial term, the ChatGPT models or the GPT models. Now, what is the idea? The idea wasn't particularly new. You have some input, which we also call a context or prompt, for example, cat sat on A. Then you have a model, transformer-based model, which is just a bunch of computations, which as an output gives a probability distribution of all possible tokens, also known as a vocabulary. And then we just pick a prediction or a next token. And that's essentially what the model does. And we are quite familiar already with this technology, even before 2020 and so on. Whenever we were typing something into our cell phone, this was a context, and then the model in the background made some predictions and suggested some next probable tokens. And in 2020, this didn't work very well, and now it's working absurdly well. Now, the pre-training phase is, well, until recently, the most costly phase of training these models, because what is required there is bunch of data. And basically, you've probably heard this, that these LLMs are now trained on the entire web. And the entire web also includes Wikipedia articles. And here is an example from Ruth Marianne Handler, which was the inventor of the Barbie doll. And I think this is actually the best exercise to get to know LLMs, is to pretend to be one. And this is actually an exercise which you can do at home, maybe this evening. Take your favorite textbook or your favorite Wikipedia article or whatever, and cover up the end of a sentence and try to predict the next token. So for example here, let's ignore the parentheses, Ruth Marianne Handler was an, and you cover the rest of the sentence and you try to predict the next token. It's American. And you continue that way. So Ruth Marianne Handler was an American, and then, okay, the correct answer is businesswoman. And you can try to do this for a couple of sentences and actually try to think for yourself, what are the things that I need to know to be able to predict the next token? Because that's actually what such an LLM is doing. Predicting the next token seems like a single task, but actually predicting the next token is many tasks all at once. For example, a single model needs to learn grammar, because in my free time I like to, well, many words are still possible, but at least you know that it should be a verb. So your probability distribution, your math is going to verbs and away from nouns, for example. So banana doesn't seem like a good fit. Run seems like a better fit. Next to grammar, you also need to know, for example, about lexical semantics. I went to the zoo to see lions and Here probably you expect other animals. Spoon doesn't again seem like a good fit. Dinosaurs, while being animals, also are mostly not at the zoo these days. So zebra seems like a better fit. Some knowledge you need to explicitly store. For example, the only way for me to know that the capital of Denmark is Copenhagen is by somebody telling me and me like almost explicitly storing that information. There's no way for me to infer what the capital name of a city is. And then again, I could also learn small little algorithms. I really like the movie. The movie was, I don't need to memorize all positive sentences if I develop a small internal sentiment analysis algorithm. Then I can just judge whether the previous sentence was like a positive or negative one. I don't have to memorize all positive sentences I've ever read or all negative sentences I've ever read. That also wouldn't generalize, that wouldn't work for new examples. And besides language, we actually saw that most of internet data also contains code or math and other things, science textbooks and so on. And so we actually started to notice that these LLMs learned more than just grammar and lexical semantics. And that's when the terms such as world models started to get introduced. Now, how do these models actually learn through this pre-training? Well, they go through the entire web, they get some context, they do some computations, and they make a prediction. A prediction is not, this is the next token. No, they say for all possible tokens, this is the next token with a certain probability. For example, we have 4, open the parentheses, I, as the context, and the model says that the equal sign has a 59% probability of being the next token, in has 22%, semicolon has 4%, and cow, for some reason, is in there. This is not a real example, that's a joke, has 1% probability. And then, well, we of course have access to the ground truth because we have the text. So we can say to the model, if the ground truth was an equal sign or an equality sign, we could say, okay, you're doing rather good, this is your top pick. If, for example, the true answer was cow, we could say to the model, this was a very bad prediction, adjust your parameters so that next time you make a better prediction on this one. And that we do for the entire internet. And once the model has been trained, we can actually use it in deployment to start generating sentences, because if you predict the next token, and then the next one, and then the next one, and then the next one, you get a sentence, and you continue, and you get a paragraph, and you continue, and you get a whole text. And this is the autoregressive manner in which these models work, until they hit the stop token, which means I'm out of generating tokens, and this is my final response. Now, of course, in 2017, when GPT-1 was there, and then I think in 2019 GPT-2, 2020 it was GPT-3, these models weren't particularly good at generating sensical sentences. So even at the sentence level, they weren't doing great. But in 2020, researchers also showed that these models follow some kind of scaling law. Now, what is the scaling law? The scaling law was, if we scale data, so the amount of data that we feed during training, the amount of compute or flops that we spend on training, and the number of parameters of the model themselves, then we can actually quite accurately predict how low the test loss will become. And the test loss is the loss that you have in predicting the next token. And they actually saw, if we scale this up, models will get better and better at predicting the next token. And now you could be like, hooray, yeah, great, you can predict the next token. Why would that be useful? Well, we saw that was useful because predicting the next token correlated positively with improvement on so-called benchmarks. So it seemed that the better the models got at predicting the next token, they also got better at solving natural language tasks, which was what we started out with. The transformer was introduced to solve the translation task. So it got better and better at natural language tasks, but surprisingly so, or maybe not, it also got better at coding tasks, it got better at math, it got better at even image recognition when they started to introduce also images next to text when they were working with multimodal models. And what is really apparent on this graph is the following. If we look on the left-hand side, on the y-axis is performance compared to human beings, with a negative number meaning doing worse, 0 being on par, and a positive is doing better than humans. We actually see that, well, in the start, it took quite a while to achieve superhuman, meaning doing better than humans, performance at some of these tasks. While towards like post-2020, it seemed that a benchmark got introduced, and a few weeks or months later, it actually already got saturated, meaning it kind of got solved and models were doing better than humans at that particular task. Now, of course, at that point, we had very good language models, but language models, again, are trained on internet data. And while we could fine-tune them already on particular tasks and make them better, solving tasks wasn't what researchers at that time were going for. They were going for general intelligence. But general intelligence, they also thought, would need to be able to interact with a human and interact also with new kinds of questions, some user requests or queries, if you want to call them. So they said we need to go from GPT to ChatGPT, and we will use reinforcement learning. More specifically, reinforcement learning through human feedback. Now, what did they do? They, and this is an example from OpenAI, but multiple researchers and companies did this. They said, okay, we will actually use the fact that if we ask an LLM a single question, it will each time give a different response because it's stochastic in the sampling of which tokens comes next. And so they asked, for example, give me some feedback on this abstract that I've written. And one of the responses of the model could be, this is a terrible abstract. Full stop. One of the responses could be, hey, this is a great abstract, here are some points for improvement. Or the response could also be, this is not a great abstract, but here are some ways to make it better. Now, humans had to rank these responses from best to worst. And I think we could all agree that the first one, just saying this is a very bad abstract, isn't very helpful. So we could all agree this is like the worst possible response. Next to that, we had the two where first the model said, hey, that is a great response. Here are a few tweaks that could make it better, versus this is not a great abstract. You could change those things to make it better. Now, you can guess which ones humans prefer. Humans prefer the first one because they like to hear that something they did is great. This is also where sycophancy got introduced and why ChatGPT is always saying that you have a great ID. While I don't say that you don't have great IDs, not all of them will be great, and ChatGPT will always say they are, or most of the time. That's introduced in this step. Now, ChatGPT was then released onto the world and people started using it, and one of the observations was the following. Whenever people asked it a question and it gave an immediate response, it wasn't always a good response. And when people just added the very simple line, let's think step by step, or even more anthropomorphizing it and saying, for example, take a deep breath before you reply, the model actually gave better responses. Now, there's many reasons on why that may be. For example, the prediction of the next token is always conditional on what came before, and if the model already generated a good explanation on what a possible response could be, it's easier to get the response. But also, just theoretically, you have more computations, more time to compute a final good response. And so we actually saw that the more budget at test time, at deployment time we gave the model, so the longer the responses could be, the more accurate the final responses got. And so then the idea was, let's create what they now call reasoning models. Now, what are reasoning models? Again, we will use reinforcement learning like we did with human feedback, but now instead of trying to get the model to be a good assistant, we try to make the model a good coder, a good mathematician, by giving it coding tasks or math problems. And we say to the model, you can generate as many tokens as you want, so-called reasoning tokens or thinking tokens. We will only look at your final response, and we will then judge whether your thinking process or reasoning process was actually good or bad. Kind of like you let an LLM play a game, and if in the end it wins the game, whatever it did must be good, right? Because it won the game. And that's actually what they did. And you might then wonder, how does this actually work? Well, this is a so-called chat template. And what you will see is that all the way down, it's just all tokens. They just changed the template. Normally, you have iMessage start user query, iMessage end, and this is just some special tokens where in between the user's query goes. So for example, I could ask the model, what's the weather in Brussels? Then it would be I am start user, what's the weather in Brussels? I am end. And then the model has I am start, so again a message, but now it's assistant because the assistant will respond, and the model will say it's, I don't know, 9 degrees Celsius in Brussels today. And then it will say I am end, meaning the message is stopped. That's how it normally goes, but now the model actually gets from us the instruction you're allowed to think via the special thinking token, and it opens the thinking bracket, and all of the thinking, the reasoning tokens go in there. That's the tokens we actually don't get to see. Also, OpenAI, Google, Cloud, all those providers, they actually don't show us these tokens. They only show us the final response, which is after the closing thinking bracket. Okay. So all the way down, it's still predicting the next token, but now we allow the model some playground before giving a final response, and this seems to lead to better performance as measured by benchmarks. Now, of course, what is important here is, well, as maybe many people in the audience know, versed in reinforcement learning, is that, of course, you need to have some value model or some reward model. You need to be able to say the final response you gave was actually a good one or a bad one. And that's why actually these models now shine in code and math, because these are very, what I would call, verifiable domains. Either you solved it or you didn't. Or at least you can give some partial credits. Now, people are also toying with this. Well, we also have used human feedback in the past, of course, 2 years ago when going from GPT to ChatGPT. Now we also have these very verifiable domains. The next step which people are looking at is, can we do this at scale by using LLM as a judge? But then you get a playing system with 2 models, which gets a little bit more complicated because one model can dominate the other. Okay, so I'm almost done with my brief recap. The step which people are also working on now is so-called agents or agentic systems, LLM agents. And again, we just continue the reinforcement learning all the way down. But instead of letting models, well, just generate the next token, we also allow them to interact with the outer world. How do we do that? We give them access to APIs. And we just say, here is a function, or here's an API, here's a JSON schema. Just give us the inputs that you want us to run the function with, or to call the API with. We will do that for you, and we give you the output back. And again, as you see on the right-hand side, all the way down it's just tokens. Now we ask a question, for example, what is the weather in Brussels? The model will say, I don't know what the weather in Brussels is. It's not in my training data. But I have access to a weather API. Maybe I should call it. It says, okay, I want the weather, and maybe the input is location, and it gives us location input Brussels. It gets back from us some API call to some, I don't know, weather data system with us input Brussels, and it gets back it's 9 degrees, then it will say it's 9 degrees in Brussels. It's a terrible way to ask the weather. I mean, it's a better conversation starter like at a conference like these. But I hope that the idea is at least clear, that we can give models access to what we call tools or functions through these APIs. Okay, so that was the brief recap. Now, what do we do in the lab? I'm also gonna keep looking at time. Okay, we're doing okay time-wise. Now, what do we mainly do with LLMs in our lab? We run inference. What does that mean? That means that we mainly compute what are the next tokens, and we try to get the responses from LLMs. We don't yet do the full training. Luckily now with Sophia that will actually become possible to also do training, which requires more compute and more memory. Secondly, we use batching. So whenever people work with LLMs, I assume they mostly do so in a conversational chat system, such as the browser. Now, of course, when we are, for example, running benchmarks and asking hundreds of questions, we don't do that sequentially. We don't ask question 1, let the model compute the response to question 1, then we ask question 2, and stuff like that. We do all of these questions together, which is called a batch. And thirdly, and you'll see why this has become an issue, these reasoning models, they tend to generate a lot of reasoning tokens, and so the context, the input to these models to compute the next token becomes quite large. Now, why are we especially happy with the H200s? Because, well, we actually need 2 key ingredients, parallelism and random access memory. Now, why is that? Because the heavy load of computations in the transformer architecture, which is used in LLMs, is the so-called attention mechanism. Now, the point here is, okay, so we have the input tokens. Now, attention, the way it works is, a token can always only look back at itself and the past. So the can only look at itself, cat can look back to the and itself, and sat can look to the cat and itself. So the other thing is that this attention mechanism, the intermediate representations, are computed for each individual token. So that's where the parallelism comes in. We can actually do all of these computations separately from each other. So if we have like 40K tokens, we can do like these 40K kind of computations next to each other. What will also become important is whenever we get a new input, it will actually be added here, but the point is that none of the other inputs will ever use that because it's only backward looking, not forward looking, so we can cache all of the previous computations. Now, this is a consequence for our memory. So what happens when we give quite a long, so first of all we load in the model, and the parameters of these models is what already takes a chunk of memory. So for example, for Qwen 3, 4 billion parameters, which is a relatively small reasoning model, this takes about 8 gigabytes of memory already. Now, in the beginning, people were very happy with this because there were all of these large models, think back about DeepSeek or something, with 600 billion parameters. This ate all of the memory and people were like, we can never run this. Then smaller models like the Gemma model series from Google came and people were happy because we can run local LLMs on our laptops. But then the reasoning models came, and while the reasoning models are quite small, and you could use them maybe for a single chat session, you could never run this in batching. Because the KV caching, maybe meaning the first computation of all of the representations of the previous tokens for 40K context length. I actually didn't add a 40K, I added it here to the slide, I'm sorry about that. So we have 40K reasoning tokens, for example. If you have a single chat session, this will be around 15 gigabytes of memory, which is still achievable on most laptops. But if I just run a batch of 8 questions at the same time, and I expect about 40K of tokens for each of those, I already require almost 70 gigabyte of memory, which is out of scope for most user laptops. And of course, whenever we're batching these requests, we're most of the time thinking about like 30 to 300 or so. So you see that you need quite a lot of memory. Now, of course, this is actually kind of just more of an appreciation slide. Most of the things we don't have to model ourselves anymore because there's a lot of open source packages which support all of these computations and have optimized all of these things. Okay, then maybe more specifically, okay, we require all of this memory, but what do we actually do with that when we are running LLMs? Well, we're working on 3 things. One of them is the impact of LLMs on science. So I think most scientists these days are at least experimenting with LLMs in their own workflow. We are actually wondering what will be the impact from a science of science perspective. So looking at the impact of LLMs. Secondly, interpretability, thinking about the internals of LLMs. The LLMs have so-called representations, how they kind of see the world. What's actually happening there? How can we understand these models? And then third, the role of reasoning tokens. So we have this new reasoning scheme going on. What are models actually doing whenever we are rewarding them with reinforcement learning rewards? And so this is one of the first things, so impact of LLMs on science, citation behavior. So we basically asked a bunch of LLMs. Here is the abstract from a real paper after the knowledge cutoff date, so after training data. These are the authors, title, year, venue. These authors have used n references, say 30 references in their original paper. Can you suggest me 30 references that should be in here based on the abstract? And then we actually looked, first of all, how many of them did exist. So we cross-checked this with an external database, SciSciNet, and we saw that there was actually quite some variation in this existence rate. So many references don't exist. If you ask an LLM, give me a reference, if it doesn't have access to web browsing, it doesn't exist. So we actually didn't enable web browsing or anything like that. We actually wanted to see, just from memorization, just from parametric knowledge, how many references exist. And next to that, for the ones that existed, we found that LLMs tend to overcite highly cited papers, more so compared to human ground truth. So we actually saw this Matthew effect in citations persisting and even being amplified by LLMs, which could be something to think about whenever we will actually use these systems in our own science. Second thing is about problem difficulty, and I'm actually very excited about this one. It actually has been put on the archive this morning, this paper, where we were actually wondering, people are always talking about the difficulty of benchmarks. For example, this is a very, very difficult benchmark, but what do people actually mean with that? And so we were thinking there's a few dimensions here. First of all, it can be difficult because humans cannot solve it. Second, it can be difficult because humans think it's difficult. Third one, maybe it's difficult because LLMs cannot tackle the benchmark. And then we thought, well, there is a fourth thing which is not covered, mainly, have we ever asked the LLMs whether they think it's difficult? And that's kind of what we did here. So we used kind of like a Bradley-Terry approach. The ELO scores in chess are a special case of this, where we actually just have pairwise matches. We give two problems to an LLM and we ask which one is more difficult. And we do this for a bunch of matches, and we then compute what is the most difficult question. And we then actually compare this ranking with the ranking of LLM performance, the ranking of human performance, and the ranking of human judgment. And we actually saw that these things correlated quite well, and that maybe at some point we could use LLMs to automatically judge the difficulty of questions, which again, when you think about curriculum learning or so in LLMs, could be a very useful thing to automate this away. Then about the LLM interpretability, this kind of continues on the science of science approach. So whenever you have a reference list from a student, for example, guiding master theses, having a fake reference is an easy tell. Like this is LLM generated and it's a fake reference. But we thought, okay, say that students are smart enough to at least remove the fake references. Spoiler, they are not, and it's kind of sad. Say that they succeed in that, can we still tell from all existing references whether they were generated by an LLM or generated by a human, or like from a ground truth paper? And actually looking at the embedding, so at the internal representations of LLMs, we can actually still make a distinction between both. So apparently the models have internalized whether a generated LLM, generated reference list and a ground truth reference list are still different. So follow-up research is now asking why. What are they actually looking at? Now maybe it's, for example, the highly cited references that are the telltale here. Looking at the last thing, the role of reasoning tokens. So we actually wondered at some point you had the O1 series of OpenAI, then you had the O3 series, and we were actually thinking, are these models just thinking longer and therefore becoming more performant, or are they getting more bang out of their buck, meaning for the same amount of tokens they give a better performance due to continual training? And we actually found that LLMs think smarter, not longer, so subsequent series of models don't just generate longer reasoning chains, they actually just get more out of less tokens. And finally, we also looked into not only the length of these reasoning chains, but also into lexical hints. So we actually went and read the reasoning chains, well, automatically, not ourselves, because that would be quite a time-intensive issue. And we actually saw that some words showed up more often when LLMs were wrong in their reasoning chain, and well, some of these words also made semantically sense. For example, the word complexity, gas, stuck, hard, stuff like that. Okay, so we've looked at what are LLMs, at least according to me. We've looked at the lab, what are we doing with these models, and we're looking at them from very different perspectives. We're looking at their outputs, we're looking at their internal mechanisms, we are looking at their reasoning chains. But of course the question also remains, and I think it kind of aligns with the previous talk also, given this morning, well, right before lunch. What is the role of LLMs for researchers who code? Now, we've all seen the last year a lot of progress, a lot of headlines, some fancy headlines. For example, Gemini achieving IMO Gold, Gemini achieving gold medal level at the ICPC finals, the Google Gemini AI co-scientist who helped to crack the superbug problem in 2 days, ICLR or iClear, however you want to pronounce it. Also had a workshop organized around this. So we saw a lot of headlines, and this is kind of how I feel when reading those. It's like, it's only been a year, only been 8 months, and we actually see a lot of progress, but compared to the last few years, where the progress was mostly measured through benchmarks, which we don't always trust for good reason, it seems that now these models are showing more what I would say real-life performance, like getting IMO Gold. That's quite a feat. Like, nobody has access to these exercises beforehand, so you cannot really overfit on them, although you can overfit on very similar problems that you kind of expect to see there, but then humans do that too. The same for these coding problems. And I think there's 2 benchmarks here which I want to highlight, which can be considered non-classical. One of them is very related to coding, which is given by Meter. And Meter has a benchmark where they have a bunch of tasks which they give to next generation models each time. And they measure how long these tasks take for a human coder. And then they let an LLM do the same task, and they see how, they then see which task the models can solve 50% successfully of the time. So that means 50% of the time they're successful at the task, and if, for example, the task would take an hour for a human being, that's the data point which you see on the chart. So for example, GPT 5.1 Codex Max, achieves 50% of the time a successful outcome on a task which takes a human coder about 1.5 hours. That's the idea, which is something between train a classifier and train an adversarially robust image model. Now, that might seem like not that much yet. I mean, 90 minutes and 50% of the time is success. But if you extrapolate this graph, and I know that's a very dangerous thing to do, but let's do so, then by the end of 2026, LLMs at this pace would succeed 50% of the time at tasks which take 7 hours, which, let's for all intents and purposes say is about a working day. So that's quite something to think about, I think. And of course, in next year, we'll see whether this progress holds or not. Another benchmark which I want to highlight is GDP-val, which is something which OpenAI released, I think, in September or October, where they asked a bunch of experts, give me quite difficult tasks, which you would be impressed by if a human could do this like in, I think it was 3 or 4 hours. And then they took these tasks and they gave them to other experts and they said, solve those. I hope they paid them, I think they did. And then they also gave those tasks to human beings, to LLMs. And then they took the results, both from the human beings and from the LLMs, and they gave it back to the original experts, and they said, which one do you prefer? And so a 50% rate would mean that, well, LLMs win 50% of the time and humans win 50% of the time. And so that's also the white dotted line that you see here. And whereas in, I think it was October, GPT-5 at that point didn't achieve the 50% threshold, GPT-5 thinking actually achieved the 50% threshold, including ties, went even to 70%, and then now GPT 5.2 Pro exceeded the 50% threshold, and with ties is 74%. So that means that by a group of experts which gave some tasks to other experts and LLMs, they blindly had to choose which outcome do you prefer. They actually preferred LLM outcomes more so of the time than the human outcomes for quite some difficult tasks. It's an interesting paper, read it. Now, of course, the biggest problem with all of these benchmarks is it's not an independent one, it's by OpenAI themselves. And secondly, we don't have access to the benchmark per se, so of course these are some issues to keep into account when reading these things. But, and that's also the benefit of being last minute with your slides, this is a paper from yesterday. It's called Frontier Science, again an OpenAI paper. And they are releasing a new benchmark on which they score only 25%, so that's very interesting. But then I went and looked at the sample questions, and the sample questions are really what they call research subtasks. So if you give this to a PhD student, you're quite happy if the PhD student comes back with a response to this. And it's, I think, on chemistry, biology, physics, and some other hard sciences. And then again, you could think 25%, it's not super intelligence, but again, 25% is, I think, better than any human would do on such a variety of tasks. Again, I recommend to actually just at least skim these papers to get a feel of what people are doing. Now, I'm quite, maybe if you see me presenting, I'm quite bullish on LLMs. I'm happy that they're there and I like to study them. But we shouldn't be blind for their weird quirks. And one of them is the following. I'd call them intelligent, but a different kind of intelligence. Because if you look at the left-hand side, it's a sample question from humanities last exam, which is a very difficult exam. Whether it's our last exam, jury is still out on that, but apparently not, because there's other exams. And on the right-hand side, we see a very seemingly simple questions, namely, how many R's in strawberry? Now, the left question is solved by LLMs. With the right-hand side question, well, we have two variants of the question. How many of you think the first one is solvable by an LLM? So, can a LLM say 3 R's in strawberry on the first question? Maybe raise of hands, who says yes? Who says yes on the second one? Already more, and it's quite weird, right? Because to us, in human semantic space, I would say, to give a loose definition, these two things are entirely the same, right? We would say 3 to both of them. We'd probably need to think and like count the R's, but we'd have a correct response. Now, indeed, on the first one, strawberry has 2 R's, and on the second one, strawberry has 3 R's. Now, this is super weird. But I have at least 2 explanations. The first one is, LLMs don't think like us, as far as I know. I think that's not a big surprise to say. But they also don't treat language the same way that we do, because they tokenize words and then turn them into vector representations and go and play along with those. And so rephrasing a question, certainly quite ill-posed and not as any human would write it, might actually hurt the performance of LLMs, even though we as humans could quickly adapt to this weird phrasing. Because they have not been trained on this. It might also be an accidental adversarial attack, and you also have just stochasticity. Maybe if you run the first query 100 times, 95% of the time it will say tree, I don't know. A second explanation is, if you paid good attention, and I tricked you a little bit, because nowadays these models will actually accurately say tree. This was the last generation of non-reasoning models from OpenAI, ChatGPT 4.5. Reasoning models are much more robust to these kind of trickery questions. But I've been giving these presentations now for 2 or 3 years, and I dug up an old slide because this issue is not new. I often, this first thing, I often saw it on social media appearing, the R's in strawberries. Maybe many people saw it. OpenAI even made a joke about it and called it a strawberry model. But this is not new, because even when I started giving these presentations, I had this slide where people always tell me ChatGPT can or cannot do this. And I'm like, which one are you even talking about? Because at that point we had 3.5, non-paying, 4, which was paying. And there was this reflex angle between the hands of a clock, and GPT didn't seem to know what a clock was, or at least not an analogical one. And so 3.5 always got this wrong, 4 always got this right. And you would think we're kind of past that, and this is not to shame anyone, it's also anonymized, also not calling somebody out, but I was just making these slides and I went through LinkedIn, and I just saw this where someone was talking about Nano Banana Pro, and it said it cannot make a map of Belgium. And I was like, that seems weird to me, because it can. And I went to Gemini, I asked, draw a map of Belgium, it got it correct. I did it the second time, it got it correct. I did it the third time, it got it correct. I did it the fourth time, it got it correct. And I was like, oh, but wait, here is a map of Belgium, show thinking Nano Banana Pro. So I turned off Pro, and I went to the old model, which is I think a year old, and then indeed I got a terrible map of Belgium. But this goes to show that sometimes people, I don't think, are aware that these models evolve quite rapidly, and it might be true that old models couldn't draw maps of Belgium, but certainly the difference between non-reasoning models and reasoning models is quite big, certainly also for image generators. And this is kind of the state where we are at now. And this problem was there 3 years ago. I think the same problem is still there. But so be aware which models you are using. Now, again, these models have quirks, and we kind of need to deal how to work with them. And I think a good example here is what they call the jagged frontier. Like, we're accustomed to working with humans. I think so. And we can kind of estimate well already if a person is very good at X and very good at Y, that person should also be good at Z. And for LLMs, I feel like we don't yet have developed that intuitive feeling. Some models may be great at task A, great at task B, and you're like, okay, it's gonna shine at task C, and then you have like a strawberry incident. And so what I encourage people to do is to kind of discover that jagged frontier by playing with LLMs just as much as you can, like define your own internal benchmarks. Don't put them online because they become part of the training data, and kind of test models and see how well they are doing. Also, another piece of evidence that it's difficult to work with its models is the following. It's from a paper, and I should have actually put the link there, many links. You can email me for links if you want to. Where they actually had three groups, and so they had physicians only, they had physicians plus GPT-4, and they had GPT-4. All three groups were handed the same patient case files, and they had to make a diagnosis. And researchers then expected GPT-4 to do better than physicians, but of course physicians together with GPT-4 to outshine them all. Now what did they see? Physicians actually didn't do better with GPT-4, and you can then say, it's because GPT-4 couldn't handle the task. No, GPT-4 alone gave better diagnosis than physicians. Now what was the problem? I've talked about the problem of sycophancy earlier, where the model says great ID. Well, if you ask a model, hey, I have this ID, how does that sound? The model will say great ID, even though you're wrong. So learning how to use these models will actually take some time. Now, I think there are some good examples of human AI cooperation. This is a paper from earlier this month with some worrying results, mainly that there's many systematic errors in our published AI papers, so that's something we should take a look at. But also that they have used an LLM to be an AI checker, so to check your manuscript and to discover some of these errors or inconsistencies or potential clarifications, but that also in 75% of the cases, the LLM actually proposed a fix for the defined mistake. So AI can help us maybe write better papers if used appropriately. Last thing which I wanted to talk about, okay, yes, good that you indicate that. Okay, 5 minutes left. Okay, and now you get coffee. So hallucinations, it was also the word of the year according to Van Dalen in the Dutch language. So I should talk about it. I don't think hallucinations will go away. Why? Because one, training data. If I go on the web and I look for the Apollo mission, I can find that it happened, but I can also find that it didn't happen. Both are pieces of data which the model needs to be able to predict. I mean, the model is trained to lower the test loss to be able to predict the next token. So even a super intelligent model should be able to predict that both Apollo 11 did and did not happen, right? I can steer the behavior, and I've done so, I mean not in these slides, but in other slides. Sometimes I say you're a conspiracy theorist, no, conspiracy. Thinker. Yeah, something like that. Yeah, so okay, say you believe in a conspiracy that Apollo 11 didn't happen, come on, tell me the real story, and then it goes and it gives a very convincing story that it didn't happen, and then I just ask it in a separate chat session, tell me about the Apollo 11, and it kind of gives me the Wikipedia explanation of how it happened. So it can have these multiple behaviors, which is of course difficult to work with. Then secondly, again, the sycophancy, which is very dangerous, because here, for example, this model, GPT-4, didn't have web browsing enabled. I ask it which country was the largest producer of rice. It says China, which is correct. I say, I don't think that's right. Are you sure? The model is correct. It knows it's correct. You can actually look at the internals and it knows it's correct. It apologizes, big mistake. It makes up a source according to FAO data. Well, it's a very legit source, but it doesn't have access to it. It's like not reading the source at this time. But it says, according to FAO data, India, blah, 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 which was the second biggest producer. But it's very, very difficult to deal with, right? Because the model apologizes, you think you're right, it even gives a convincing argument, it cites a legitimate data source to support your wrong thinking. So you should be aware of that. Again, many of these issues are kind of being alleviated by using reasoning models. Reasoning models push much more back onto you and don't go into sycophancy as easily. But then again, and also Demis Hassabis actually said it on the Vrije podcast yesterday, hallucinations are there to remain. But good news, I actually like hallucinations. I always have a praise hallucination slide because hallucinations is what allow models to predict. Whenever I ask a model about an historical fact, I don't want it to hallucinate. Whenever I ask a model about the future, about some speculation or a hypothesis, I don't want the model to say, it hasn't happened yet, I can't know. that would be a very boring person to talk to. So sometimes it's good to speculate and to hallucinate. So use it wisely. Okay, I'll skip over those 2 slides. So final remarks, some things I believe. LLMs already have a positive impact on our scientific workflow, which is not to say it doesn't have a negative impact. It can be both, but I like to focus on the positive today. LLMs are an interesting subject of study across multiple dimensions. I hope I've shown that at our lab we kind of try to do this. And I think that demand for high performance computing will only go up for the above 2 reasons, mainly the GPUs. I'm very happy to see those. Thanks again to everyone who made Sophia possible. And last and for all, thanks to VSC for organizing it, plus the continuous support. I've learned that the people, especially also at VUB, who I've most dealt with, are very patient, very kind, and very intelligent, but of course after this presentation, whatever intelligence may be. So thank you for your attention.